let's talk about change of variables. So in the past, we've encountered problems where we were setting up a double or triple integral, and the region was complicated enough that the bounds on our iterated integral ended up giving us a difficult calculus problem. Change of variables is a technique that sometimes simplifies those issues. So let's start with an example of a double integral. So here we're studying a region in 2 dimensions, and the region is a parallelogram spanned by the vectors 3, 1, and 1, 2. So let's say that we know that density in this parallelogram is measured by the scalar field F equals 3x squared plus y, and the units here are kilograms per square meter. Well, if we wanted to calculate the actual mass of this region, we could do so with a double integral, but if we look closely at this region, we realize that we're in for a little bit of effort, because in this region, if we wanted to describe it with an iterated integral, we actually need several iterated integrals. If we were to use x slicing, when we slice vertically throughout the region, well, sometimes we enter through this bottom line and then exit through this top line, but at other points, perhaps if we slice between 3 and 4, we enter through this other line and then exit through a different line. So there's like lots of corners in this region, so setting up one double integral won't work. So let's take a closer look at what these edges are defined as. So each one of these edges is defined by a line passing through 2 points. So the line passing through the origin and the point 1, 2 is y equals 2x. The line passing through the origin and 3, 1 is y equals x over 3. The line passing through the point 3, 1 and 4, 3 is y equals 2x minus 5. And the line passing through the point 1, 2 and 4, 3 is y equals quantity x plus 5 over 3. So here at least we have some equations we can work with when we set up our double integral. So to calculate the mass, we need 3 iterated integrals here. If we're using x slicing, we might choose a slice between x equals 0 and x equals 1, where the rule for entry is through y equals x over 3, and the rule for exit is y equals 2x. But there's also slices between x equals 1 and x equals 3. Here the rule for entry is still y equals x over 3, but now the rule for exit is y equals quantity x plus 5 over 3. And if we slice between x equals 3 and x equals 4, the rule for entry is y equals 2x minus 5, and then the rule for exit is y equals quantity x plus 5 over 3. So to calculate the mass, we need 3 iterated integrals. Our first iterated integral accounts for the slicing between x equals 0 and x equals 1. So that's where the entry is y equals x over 3 and exit is y equals 2x. If we slice between 1 and 3, that's between y equals x over 3 and y equals quantity x plus 5 over 3. And then if we slice between x equals 3 and x equals 4, that's y equals 2x minus 5 up to y equals x plus 5 over 3. So to calculate mass in this problem, we need 3 iterated integrals. And if we do all the calculus here, there is an answer, and we end up getting 80 kilograms. Okay, so this is a problem, because parallelograms are not complicated mathematical objects, so it shouldn't be difficult to do this calculus, but it is. So how are we going to solve this problem? Well, one idea says maybe we can change variables so that we can work with a nicer region. So let's look at this idea in more detail. So remember, the region we're working with is this parallelogram, and the density function here is f equals 3x squared plus y. So let's introduce a change of variables function. So the change of variables function we're introducing is this function from R2 to R2, which we're calling capital T. And the idea is that T helps us introduce new variables. This is u comma v. And the formula we're giving for T is the first coordinate is 3 times u plus v, and the second coordinate is u plus 2 times v. We'll see where this formula came from in a moment. But the idea is that we're introducing two new variables, u and v, that help us understand xy space. So what we're doing is we're suggesting that we set x equal to the first coordinate, 3u plus v, and we're suggesting that we set y equal to the second coordinate, u plus 2 times v. So here's a visualization of this change of variables. So let's imagine that we have two dimensions where the axes are labeled by the variables u and v. Well, where did the formula for t come from? What we're really doing is we're constructing a matrix here where the columns are given by the two vectors that span our parallelogram. So the parallelogram we started with was spanned by the vectors 3, 1, which is the first column of this matrix A. And then the second vector here is 1, 2, which is the second column of this matrix A. The idea is that if I take this matrix we've constructed and multiply by the vector of coordinates u, v, we get the formula for our change of variables here. So in essence, what we're doing is we're relating the unit square in uv space to the parallelogram we're interested in xy space. So if we take a look at these two regions, the idea here is that we would much rather work with this square on the left, which we're labeling d star, than work with the original parallelogram d. And this change of variables function, capital T, is a function that helps us relate information inside of d star to information inside of d. So the natural thing to do here would be to compose our density function that we developed earlier with this change of variables function. When we compose these two functions, here we're taking f of t of uv, and we're replacing our x's in the density function with the quantity 3u plus v, and we're replacing the y's with the quantity u plus 2 times v. Well, the original formula for f was 3 times x squared plus y. When we compose f with t, we now get 3 times the quantity 3u plus v squared plus the quantity u plus 2v. And so now what we might naively do is say, well, after making these substitutions for x and y, let's use this as our density function and then integrate over the unit square in uv space. Let's see what happens when we do that. So now, instead of taking a double integral of the original f over the region d in xy space, we're now going to take a double integral of our composition over the unit square in uv space. So now we're taking a double integral of the density function 3 times the quantity 3u plus v squared, because that's what x is equal to, plus the quantity u plus 2v, because that's what y is equal to. And now, instead of needing 3 different iterated integrals, we're simply integrating du dv, where both variables are ranging between 0 and 1. And when we do all the calculus here, here's the answer we get. We end up with 80 divided by 5. So this is an issue because we saw previously that the mass of our region, of the region D we started with, is actually equal to 80. But now when we implement this idea, we have messed up our answer. The answer is now 80 divided by 5. But I want to point something out. By doing this problem and getting 80 over 5, there's actually something happening here. The 80 in the numerator here is the mass of the domain that we care about. That's the mass of D, which we calculated previously. And where's this 5 in the denominator coming from? That's actually equal to the area of the parallelogram we're interested in. And remember that in two-dimensional geometry, areas of parallelograms are determinants of matrices. So the reason we know the area of this parallelogram is 5 is because that's what the determinant of our matrix A is in this problem. So there is some relationship in this information. The mass of the region D star with this idea is equal to the mass of the region we cared about divided by its own area. So it seems like there's some relationship after this change of variables where our new integral is producing the mass, but it's divided by the area somehow. So even though this is a good idea, it doesn't actually answer our problem or address our problem because we end up with an answer that's sort of thrown off. But it is useful to notice that this answer is related to the actual answer, which is 80. So what's the lesson here? By changing the variables in our problem, we simplified the calculus, but this came at a cost. The original integral, which was the double integral of our density function over the region D, that was the actual mass calculation we wanted. And when we did the calculus, we needed to break this up into 3 different iterated integrals. And when we did all that work, we got 80. Well, when we changed variables by introducing this function capital T, we composed the density function with capital T and integrated over the nicer region. That was D star, which was the unit square in UV space. Well, the issue was that the calculus here was easy, but we got the wrong answer, whereas in the original integral, the calculus was difficult, but we got the right answer. So one of the things we'll need to do is we'll need to figure out, well, how can we tweak this formula on the left so that the calculus is still easy, but the answer is actually right? So that's what the change of variables formula will address when we get there. I want to look at another motivational example. So in the second motivational example, I want to look at a different region with a different density function. Here, let's say that the region we're studying is this circle, and let's say that the density is x squared plus y squared. And the circle we're studying here is the circle in the xy space centered at the origin where the radius is 2. So the idea here is that if we were to do a double integral, we could do this double integral with one iterated integral. There is a bottom part of the region, which is y equals negative root 4 minus x squared. And there's also a top part of this region, which is y equals positive root 4 minus x squared. So to calculate mass in this scenario, we don't need multiple iterated integrals. We can set this up with one iterated integral. If we used x slicing, say, well, we would be integrating dy dx, where the lower bound for y would be negative root 4 minus x squared, and the upper bound for y would be positive root 4 minus x squared. The x's in this region, because this is a circle with radius 2, would range from x equals negative 2 to x equals 2. So now we have a perfectly good iterated double integral, and we can do the calculus here, and we end up with an answer, and the answer happens to be 8 pi kilograms. But if we look at this for a moment, we realize that there is some effort that goes into this calculation. The bounds for y here are negative root and positive root something, and whenever we're working with roots in calculus, things get a little bit tricky. So I'm sweeping the calculation under the rug here. There's a lot of effort that actually goes into the calculation. So we get an answer of 8 pi kilograms, but that comes after a lot of work. So what's the problem here? Well, circles are very ubiquitous mathematical objects. So if we're going to have a theory where we do calculus, problems over circles shouldn't be difficult. So the fundamental issue here is that integration over circles should not be difficult. Well, what's the solution to this issue? Well, let's change variables, just like we did previously, so that we end up working with a nicer region. And if we're talking about circles, well, it's important to remember that there's a coordinate system that's designed to be nice from the perspective of circles. And namely, that's the polar coordinate circle, or polar coordinate system. So remember, the polar change of variables is a relabeling or an introduction of new variables r and theta to describe regions in xy space. In the polar change of variables, we set x equal to r times cosine theta, and then we set y equal to r times sine theta. the polar coordinate system makes working with circles much easier. So we were just studying a circle centered at the origin of radius 2. Well, from the polar coordinate perspective, the idea is that the angles in this region, the angles made with the positive x-axis, range from 0 to 2 pi, and the radii throughout this region range from 0 to 2. So the circle of radius 2 in the xy space is related to the rectangle in r theta space, where r ranges from 0 to 2 and theta ranges from 0 to 2 pi. So what if we implement our concatenation idea again? Well, the density function for the region we started with, this region D, was f equals x squared plus y squared. When we compose f with this change of variables, what we're doing is we're replacing x with r cosine theta and y with r sine theta. We've seen before that with these introductions, x squared plus y squared is equal to r squared. So we can set up our new integral, which is the integral of the composition of f with the change of variables function. And we're now integrating over d star, which in r theta space is the iterated integral where the bounds are all constant. Here, r ranges from 0 to 2, and theta ranges from 0 to 2 pi. So now we have a much simpler iterated integral. We're simply integrating r squared from r equals 0 to r equals 2, and from theta equals 0 to theta equals 2 pi. The calculus here is not difficult at all, and when we do it, we get an answer, but again, there's an issue here. The answer we're getting is 16 pi over 3, where we saw previously that the answer should be 8 pi. So once again, we had an idea and something's going awry here. So what's the lesson? Well, again, by changing variables, we simplified the problem, but this came at a cost. The original integral we did was on the right here. The original integral was our density function f over the region D, and when we did that calculation, we got 8 pi. Well, when we changed variables and used polar coordinates, we were no longer integrating just f because we were replacing x with r cosine theta and y with r sine theta. So really what we're doing is we're changing the density function by composing the original f with the change of coordinates. And then instead, the reason we're doing this is because instead of integrating over the complicated circle, we can now integrate over an easier rectangle. But just like in our parallelogram example, the issue here was that this idea produced a problem where the calculus was easier and we got the wrong answer. Whereas the original problem had difficult calculus, but we got the right answer. So what we need to do is we need to remedy this situation. The idea here seems to be so good that there must be a workaround where instead of integrating and getting the wrong answer, we integrate and get the right answer.